Hi, I'm Trevor, author of Lamorna Engine, a light 3D game engine featuring a software renderer, which you just saw running. Today I'd like to talk through the code that powers the back end of the renderer. Lamorna Engine has a sort middle binning architecture, which means that triangles coming off the geometry front end are written to buffers assigned to screen space bins. The bins improve cache access patterns and allow the division of labour among threads. Lamorna Engine expresses the processing of a bin as a job, which is submitted to the thread pool. The entry point for the thread is this function render screen bin, which contains the following subfunctions. Process bin triangles is where the bulk of the work is done, fetching triangles from the bin buffer, performing triangle setup, rasterization, attribute fetch and shading, and finally pixel shading. Depth fog applies the distance fog you saw fading in and out in the demo. This is run after all the triangles have been processed because it uses the depth buffer to modulate the color buffer. Right frame buffer copies and swizzles the bin color buffer down to the DirectX drawing surface, and clear bin buffer clears the bin depth buffer. Looking at the function parameters, the model manager data structure will be used for fetching the mesh vertex attributes such as texture and color coordinates, which are not binned by the front end. The display data structure contains the triangle bin buffers as well as the color and depth buffers for the bin. We also have the X and Y screen space coordinates for the top left hand corner of the bin. So let's descend into the process bin triangles function. Now the first broad task of this function is to fetch out triangles from the bin, but first some pre-processing. The triangles have been binned by draw call, and first we're going to discover what draw calls we have present in the bin and sort them so we can read out the triangles in draw call order. This is done as an aid to visibility processing. The engine uses a hierarchical Z buffer to accelerate hidden surface removal, and this works best when triangles are submitted in a particular depth order, closest to the camera first. Depth sorting individual triangles would be too expensive for even the modest scenes that we have here, so I ensure that meshes which are more likely to be occluders in a scene, such as the world map meshes, are in lower numbered draw calls, and sort so we render those draw calls first. And that's what we're doing with these two blocks of code. So with our draw calls sorted, we can step through them and read out their binned triangles. Note that the vertices of our bin triangles are in screen space, and each vertex has a barycentric coordinate associated with it that has been clipped and projected by the front end. We process 4 triangles at a time using SIMD, and this first step computes the depth interpolance, which we will use within the rasterizer for our hierarchical depth test. We don't compute interpolance for the other vertex attributes, such as color and texture coordinates, as these will be derived from barycentric coordinates in the shader. To find the depth interpolance, we invert a 3x3 matrix composed of the triangle vertex positions. We find the determinant of the matrix using the triple product. We multiply the transpose matrix through by the reciprocal of the determinant, yielding a matrix that maps from a parameter to interpolant. Then we vector multiply through by the depth parameter. This is done using SIMD. These are overloaded operators hiding the vector intrinsics, so the code flows and reads like scalar code, except we're processing 4 elements at a time. Note the determinant that we calculated before is proportional to the triangle area, so we save that off as we will use that later. Now we get down to the real business of drawing this triangle. We will step through each of the 4 triangles. We have done interpolance setup on one at a time, rasterize them down to a stream of fragments, and shade those fragments. So we have a raster setup, and then this function calls the actual process of rasterization. We won't look at the raster functions, that's for another video, but we do need to talk a little about the process. we use a hierarchical descent rasterizer to determine pixel coverage, where local screen space is divided up into a tile hierarchy against which the triangle edges are checked recursively and marked as included or excluded. The raster fragments are emitted according to their tile size, 64, 16 and 4x4 pixel blocks respectively, where the larger blocks are emitted from the interior of the triangle and the smaller blocks from around the edges. Blocks that straddle the edges of the triangle contain a bit mask describing pixel coverage. As mentioned earlier, the rasterizer also checks fragments against a hierarchical depth buffer and will discard ones that are occluded. Now we approach pixel shading, but a few things first. We still haven't fetched or shaded any vertex attributes, and the reason we defer that till so late in the pipeline is right here. If there are no valid fragments emitted by the rasterizer for the current triangle, we move on to the next triangle, avoiding the cost of fetch and shading for a triangle that is ultimately not drawn. If there are valid fragments, we begin by fetching out the color and texture coordinates from the parent mesh using index data that was binned with the triangle by the front end. If the attributes are marked for shading, we will do so, where shading is multiplying the vertex attributes by a transform matrix. This allows us to animate the color and texture coordinates of a mesh each frame. We do some shading setup here, getting the attribute and barycentric deltas, broadcasting values out into the vector registers, and then we call this function which will process the raster fragments for shading. I'll step down into that. The shader operates on a block of 4x4 pixels and it expects barycentric values for each pixel. So this next step is continuing the work of the rasterizer in some respects, in that it takes the recorded edge value for the tile corner and uses the step tables generated in raster setup to step the edge values recursively down to the level of a 4x4 block. The edge values will then be broadcast out to pixel centers and normalized to barycentrics by dividing by the triangle area. So that is what is happening here. And if we take the 64 by 64 pixel tile stream as an example, we step edge values to the corners of the 16 by 16 pixel tiles, which are contained within that 64 by 64 block, and then recursively step down into each of those 16 by 16 tiles, and do the same there for the 4 by 4 pixel blocks contained within each of those 16 by 16 tiles. So that's the 4 by 4, and then we finally step the edge values from the tile corner to the 16 pixel centers. Now here we are, there is the pixel shader routine, which we can finally call. Now, before we look at the shading code, there's a few things to mention. To keep things simple, Lamorna Engine applies the one fixed pixel shading routine to all fragments. This routine interpolates 3-channel color across the fragment and adds that to a point-sampled, MIPT-mapped texture read. We use SIMD to process a block of 4x4 pixels, and the code is written as a monolithic inline block, which I will just show you in its entirety by scrolling down to the bottom of the function and back up. So you can see that that is a monolithic block of inlined code. Any use of loops or function calls here has an adverse effect on performance. There are 2 types of barycentric coordinates used here. Firstly, the screen space barycentrics that we derived from the edge values coming in from the rasterizer. The second type are the barycentrics that have come in from the bins, which were clipped and projected by the front end. Now, why 2 sets? Well, the first type can be used to derive perspective correct, clipped barycentric values from the second type. Sending barycentric coordinates through the pipeline as vertex attributes, where they are clipped and projected, means we don't have to do that for any other vertex attribute. That means we can defer attribute fetch till just prior to shading, avoid computing attribute interpolants, and we don't pay the cost of unprojecting each attribute component in the shader. So let's step through the shader code. Here we normalize the input edge values to screen space barycentrics by dividing through by the triangle area. Here we compute the screen space deltas by taking the dot product of the screen space barycentrics and the depth deltas. We convert the bit mask, which describes pixel coverage, to a vector lane mask. Here we load the tile depth buffer. The bin depth buffer. I'll just get the nomenclature right. We compare the triangle screen space depth to the values from the depth buffer and combine the resulting lane mask with the pixel coverage mask to create a composite valid pixel mask. And we store this composite lane mask down as a bit mask, and we create a blend of the triangle and depth buffer values using the composite mask, preparing it for write down back into the depth buffer. And then we find the maximum Z value for this current 4x4 block, which will later be broadcast up the depth buffer hierarchy. And then we write down our new depth values into the depth buffer. Now, if no pixels in our 4x4 block have survived the depth test, we exit the shading routine early. If not, we continue, and here we take the dot product of our screen space barycentrics and the binned barycentrics, multiply through by the reciprocal of our screen space depth to yield these perspective correct clip space barycentrics. Now the next section is concerned with computing color values for each pixel. We take the dot product of our barycentrics with each of the three color components, R, G, and B there, to yield clip space perspective correct values for each pixel. We clamp the color channel values to prevent over or underflow, and convert each channel value to integer and build out our packed 32-bit color value ready for write down into the color buffer. Now, the next section is concerned with fetching the texture values for each pixel. We take the dot product of our barycentrics and the two texture coordinate components, U and V, to yield clip space, perspective correct texture coordinates, and store them down for the moment, because now we are going to compute the mipmap level for the current pixel block. Ideally, this is calculated per pixel, but this is where the lack of a feature complete vector ISA hurts, and I have to resort to scalar code. We find our screen space derivatives, compute the texture space area, take the log of that value and clamp it. This mipmap level then informs the texture dimensions which we set here and broadcast out to our vector registers. With the mipmap level computed, we return to fetching our texture data. We take the normalized perspective correct U and V values and multiply them by our texture dimensions. We convert these coordinates to integer values and clamp them to prevent spurious memory reads. We compute the final index into the texture and drop down into scalar code to do the actual read in of the texture color values. We load the color value, we load the color buffer values in. We add the color channel values to the texture color values and blend with the existing color buffer values according to our valid lane mask. And we store the resulting color values down to the color buffer. And that is the end of the shading routine. But I would like to return now to our process fragments function. Let's just do that. We've seen how we step down through any 64x64 tiles which are present in the fragment stream. We do that same stepping down for all the 16x16 and the 4x4s tiles as well. And that completes the shading of the different fragment streams. We saw how the shader returns a maximum depth value for all valid writes to the depth buffer. This value must be propagated up the depth buffer hierarchy. We do this by bit marking which tiles are visited as we process the raster fragments, and then here at the end of the routine, step the maximum values up for the 4x4 blocks through the hierarchy. So we step the 16x16 first, and then the 64 up to the 64x64s, using SIMD to process that once again. Now finally I want to return to our render screen bin function, which is there. So our process bin triangle function exits when all the triangles in the bin have been shaded. So we now have a fully populated depth and color buffer for the bin. I'll ignore the depth fog function because that doesn't relate to base rendering, but I want to look at right frame buffer. This takes the bin color buffer and writes it down to the DirectX surface associated with our game window, which has been unlocked for writing just ahead of backend processing commencing. The color and depth buffers are written to using a tiled approach that improves memory access patterns, and the data has to be unswizzled prior to copying down. We step through the destination buffer 8 pixels at a time, and at each step we bit interleave the X and Y values of our source buffer to produce a so-called Morton code, which is the index into our swizzled source data. And we use SIMD to speed the copying process there. Final step for rendering in a bin is to clear the bin depth buffers. Pretty straightforward. Here we zero out the depth buffer hierarchies using SIMD. It is worth noting that there need only be as many bin buffers as there are worker threads, as you can see here. So we save some memory in comparison to having those buffers as partitions of larger screen size buffers. The final thing to note is the parallelized nature of bin rendering. The processing of each bin is expressed as a job and submitted to the thread pool. Since triangle data is exclusive to each bin, many bins can be rendered simultaneously. Well, that concludes our overview of the back-end rendering code. For more information and to download the demo, please check out my website and follow me on Twitter. Thanks for listening.